Thank you everyone for joining. My name is Paul Lappas. I'm a product manager on the Delta Live Tables team. I wanted to start by saying, unfortunately, Michael Armbrust will not be able to make it. He got COVID, and he made the wise decision to not come to a packed conference. So he sends his best wishes, and he's told me to say hi to all of you. Before I get started, I have the product safe harbor agreement. Everything we say here today is for informational purposes only, and nothing that I say is a commitment. So I wanted to start by introducing the data intelligence platform, which allows your entire organization to use data and AI. It's built on the Lakehouse to provide an open and unified governance structure for all of your data, and it's powered by the data intelligence engine that understands your unique data for your unique organization. All this adds up to our vision of democratizing data within your organization for all of your customers and your employees, so that we can ensure that your teams are as productive as possible in making decisions with their data. Now, it's no surprise to many of us in this room that AI is on the top of our mind. Generative AI has seen explosive growth in the past couple of years and is slated to grow by exponentially in the next few years. And this has really put more of a focus on companies to acquire and get good data from everywhere that it sits in their organization. Data was always a strategic asset, but these new demands on accessing all of your data have made data engineering even more important. So not only for Gen AI, but data is important for customer satisfaction, for building better products, for making your operations more efficient. And companies rely on analytics to make decisions and make predictions on their data. And all this is supported by data engineering teams. Now, the medallion architecture that Databricks has talked about for many years is a really useful data design concept to think about how to structure your data pipelines as they move from left to right, from bronze, where it lands into the lakehouse, to cleaning and refining in the silver layer, finally to modeling and presenting it out to your users and your customers and your applications. And the goal is to improve data as it moves left to right. But it's not always easy to build this when data engineering is really, really complex. What data engineers really want to be able to do is write business logic, write transformations on their data. But they end up spending a lot of time on toiling, on creating and maintaining and managing data pipelines. Turning queries into production pipelines is really, really hard, and we see the challenges across two dimensions. One is that to build reliable streaming pipelines, you need to stitch together tools from many, many different vendors. So you've got EMR and ADF and Glue and Oozie, and you need subject matter experts to be able to pull all of this together and make these systems talk to each other effectively. It means that whenever you want to make changes to these pipelines, these folks have to be involved. It makes it harder for you to make changes, ultimately harder to debug issues when they go down. Once you do get everything working, you have to make sure that things run on time and on budget. Every organization has special requirements as to how fast data should be produced and what budget you have to maintain that under. It's really hard to do this. You end up writing your own monitoring tools, your own debugging tools, and ultimately, it's time that you would rather be spending on other tasks. This is why we built Delta Live Tables. Delta Live Tables is an ETL framework that automatically manages all this complexity for you so that data engineers and analysts can spend their time focusing on providing a declarative description of what they want their data to look like, and DLT will handle all the complexity of error handling, scaling, monitoring, operations. And ultimately, this means that you can spend more time on other tasks. DLT handles scaling, failures, retries, making sure that your data is always in the correct state if there are issues. It looks at all of your code and makes sure that things run in the correct order. It has real-time observability logs, native tools for data quality. And one of the really cool things that I'm going to talk about today is now for the first time with Serverless, these pipelines are incremental end-to-end, from ingestion to transformation. Now, Databricks, what is declarative programming? I think I mentioned this a few times. Declarative programming basically means that you just tell the system what you want the outcome to be, contrasted with traditional imperative programming, where you assume that the system is dumb and you have to tell it explicit, step-by-step instructions about what to do. A great example is iterating through a column of values and summing them up. In a declarative system, you just select sum from that column, and the system will do the needful things to make sure that that result is materialized as quickly and efficiently as possible. The nice thing about declarative systems is that we can improve the engine over time to make these things run faster and more efficiently for you, so that magically, all of a sudden, one day, your queries will run faster. You won't have to make any changes. Now, there are still use cases for imperative programming. It's okay that all your code is not declarative. 20% of use cases will always be imperative, probably. Like, you'll always have some bespoke stuff to ingest where you'll need to write custom Python code for that, or egressing to some application that requires some imperative programming. But the point is that you have choice on the Databricks platform. As a rule of thumb, if you're using SQL, that's declarative. If you're operating on a structured streaming data frame, that's imperative programming. Otherwise, use jobs and notebooks. Now, Databricks gives you choice of how to leverage DLT's declarative capabilities across the lakehouse. Let me sort of walk you through these. At the simplest layer, we have simple and opinionated primitives for ingesting data. Data ingestion is really easy, right? You're just pointing to a source and a destination, and we're just copying data in for you. It's so easy, we're gonna build a point-and-click UI for any source that we connect to. Here, I wanna plug, there's a session tomorrow. My colleague Elise is talking about ingestion connectors at 11:30 tomorrow. We'll also go deep on some of the capabilities that we're announcing at DICE. But say you want to do some transformations on that data before it lands in Delta, or like right after it lands. That's what streaming tables are for. You can create a streaming table, you define a SQL expression or a Python expression, do some basic cleaning, some basic filtering, and it lands in Delta really, really quickly. Materialized views are for complex transformations in data modeling. They're refreshed incrementally, but they're always correct. They will always propagate updates and deletes and changes from their source. When you have multiple streaming tables and materialized views in a pipeline, you can run and author your DAGs with DLT pipelines. And then underpinning all of this are some cool new capabilities I'm going to talk about today, flows and syncs, which allow you to really, really express your structured streaming, your pipelines in a way where you can evolve your sources, you can evolve your destinations, and everything is built on top of these core primitives for DLT. So you can choose to use any of these depending on your use case. Now, what is a streaming table? It's really a simple way to stream and perform low latency transformations on data. It's built on top of the autoloader, on top of structured streaming. Ultimately, it enables anyone to do streaming. You can just write one simple SQL statement and build a streaming pipeline with streaming tables. It's really, really scalable. They're powered by serverless infrastructure. They'll scale, the infrastructure, the compute that underpins the streaming table will scale horizontally and vertically to handle any data that you throw at it. And it opens up real-time use cases anywhere on the lakehouse. You can ingest data continuously with a streaming table and land it into Delta with a latency of seconds. And materialized views work with streaming tables downstream to perform complex transformations. Their performance improvement features. Data is pre-computed in the materialized view. The view will always represent the data in the query that it's implemented with, that it's defined with. But queries to the view are really, really fast because they're pre-computed, so they're great for dashboards, for ETL, for query acceleration. And with Enzyme, that I'll talk about today, they can be incrementally refreshed so that you can get really, really fast data no matter how big the view is. Now, many of us in this room use DBT. Could I get a show of hands of who uses DBT? Great. We love DBT. DBT is really, really, really popular on the Databricks SQL platform. And it's become one of the most popular ways for users to build pipelines in Databricks SQL. DBT now has native support for Databricks streaming tables and materialized views as of DBT Core 1.8. So you can get the best of both worlds. You can stay in the DBT environment. You can target streaming tables that get launched on the platform where you can do native streaming ingestion without needing to bring in other vendors or do copy into batches as the alternative. And with materialized views, because they incrementally refresh automatically, you won't need to deal with telling the system how to merge your changes into your models. So this is something that we're really excited about. So I'm really pleased to announce the GA of materialized views and streaming tables in Databricks SQL. This will be coming in an announcement in just a few weeks, early July. And this has been something that's been really exciting for us to launch over the past year. And now I want to introduce my colleague Julia, who's going to talk about and show us some cool new capabilities about MV's observability.
My mic working? Okay, I'm just gonna assume it's working.
Yep.
All right. I'm Julia, and I'm gonna be showing you all a demo of some exciting new capabilities that we're launching soon that'll make it easier than ever to observe your refreshes, refresh schedules, and errors for your materialized views and streaming tables in the Databricks UI. So for my demo, I'm gonna be playing the role of a data scientist who was asked to create a dashboard that updates hourly that shows some taxi trip trends. And I'm going to walk through that flow as well as some debugging flow that uses some of these new features. So let's get started with this demo. Okay, so I'm first going to create a materialized view in the SQL editor. And I'm going to schedule this view to refresh with cron every hour at 30 minutes past the hour. So just writing this query, and then once it's, is it? Okay. Let me just make sure it is working. Okay, I need to press the play button. Okay, it's working now. Okay, so I'm running my view, and now I'm gonna go check out my newly created table in the Catalog Explorer page. And here you can see on the right side, there's some new features on the right, like refresh status and refresh schedule. And it actually translates the cron schedule into human readable English so that anyone who's using this does not need to know cron to understand the schedule. Anyone can see that it's 30 minutes past the hour. And so yeah, now I'm creating my dashboard. I sped some parts up to make it a little bit less boring as I'm going through all the steps of creating the dashboard. But basically I'm just pulling from that materialized view I just made and adding some charts that'll show some trends like ride duration every hour and the trip distance every hour. And then I'm gonna schedule it to update every 30 minutes, and that's all for my dashboard. Looks like I'm done with the dashboard, and that's it. But the next day, I get an email from the PM saying the dashboard is broken. He says, the dashboard is broken, it has not updated for 4 hours, please fix. So yikes, I'm gonna have to debug this a little bit. So what I do is go into that Catalog Explorer page again, and I see that the refresh status does indeed say failed. So I'm gonna go click on the See Refresh Details button to see what's going on. And that takes me to the details page where I can click on the error in the event log. That'll show me some more info about the error. And looks like it says user does not have select on table name. So looks like I somehow lost access. So I'm gonna ask my colleague who owns the table to grant me access again. So he grants me access, so everything should be good. I'm gonna pause this right here and, side note, I want to point out that in Databricks, you can still query materialized views, even if you've lost access to a table or if the table's been deleted or whatnot. So all the data that was there is still there and still in the dashboard. It's just like new updated data will not be showing up. So it's still perfectly usable. Okay, I'm going to continue debugging this. So, I think I accidentally restarted my video. Where was I? How do I make this? Sorry, I'm trying to go back to where I was. Okay. So going back a few seconds, basically what I did was ask my coworker for access again, and he granted me access. So my next refresh should work, hopefully, since the error has all been fixed. So I'm gonna wait for the next refresh and look in the Catalog Explorer page to see what the status is. So I'm gonna head over there, and looks like it is green, completed, so that means it was successful. And it even tells me the timestamp and how long ago it was. So now I can also confirm by looking at refresh details again. Here I can see more info, and then I'm gonna check my dashboard to see if that's been fixed. So I go into my dashboard, see if the update is run, and yes, it looks like the data is different with new updated data with the new timestamps. So it looks like it was fixed. So I can now tell my PM that it's back up and ready to use with all new data. And yeah, as you can see, that was pretty easy to debug and fix all that with just a few clicks. And I'm really excited for you all to use these new features once we release them, and let us know what you think. Thanks everyone for listening.
Wow, that was awesome. I really want to go use that more. Excellent. Thank you, Julia. We talked about STs, materialized views. Now I want to talk about pipelines. So pipelines are three things. When you think about pipelines, think about three properties of them. One is their source code. You create a file or a notebook, and you write down all your create streaming table, your create materialized view statements. It doesn't really matter what order that you write them in. You can mix Python and SQL, not in the same file. You have to have a different file with Python, a different file with SQL, but you don't have to worry about telling the system what the dependencies are. It will automatically resolve those and build that graph that you see in the UI. That graph emerges from your code. You're not pointing and clicking it. The second thing that the pipeline is you tell it where the data should be stored. So today, there's a single location for all the tables in the pipeline. I'm going to be announcing some changes to that later in the presentation. But ultimately, there's a location for the data and the schema that it should go in. And then finally, there's a configuration for the pipeline. This is where you tell us the compute, you tell the system the permissions of the pipeline, any key value pairs that, keys and values that you're passing into the pipeline that you can then use in your source code, and other things related to the runtime of that pipeline. When you run, DLT will just resolve those tables, run them in the correct order, deal with retries, deal with failures, and scaling. So it's really, really easy to get started. So a flow is a new concept. I think we haven't talked about it last year, but we've released it over the past year. And a flow is a new primitive. It's really the easiest way to evolve structured streaming, to work with structured streaming. Like I said earlier, a streaming table is underpinned by the structured streaming APIs. What flows allows you to do, so before flows, you really could only assign a single query to a streaming table, which meant that if you wanted to add a source or you wanted to evolve that query in a way where you had to change its checkpoints, you had to do a full refresh. That was kind of a non-starter for really large streaming tables. With flows, you can now create additional flows that target existing streaming tables. This makes it really easy to do things like backfills and corrections, add new topics as sources to your streaming tables. And this works for both append-only flows and flows that are change flows, like the apply changes into flows. So this is something that we're really excited about releasing. Syncs are a brand new concept that are currently in a private preview. If flows allow you to evolve the sources of your tables, a sync is a way for you to tell us where you want the data to go. By default, it's Delta, it's Unity Catalog, but you can create a sync, like a Kafka sync, for example, and you can target your pipeline to sync to that. One of the really exciting things here, many of you in this room have probably asked for the ability to sync to for each batch APIs. That's coming with this capability. So you'll be able to sync your events to for each batch within DLT. So I'm really happy to announce the GA of Delta Live Tables with serverless compute. This will be coming also in a few weeks, so please look for the announcement. DLT with serverless compute has been in a preview state for quite some time. We have hundreds of customers using it at scale, and so we're really excited about this new capability on the platform. So I want to talk about DLT in general, its benefits, but also there are some unique things to serverless that you can only get if you use serverless. I wanted to take another quick show of hands. Who in this organization has used Databricks and is able to use serverless on Databricks. Their companies are great. That's a pretty good number, thank you. So, more and more we're hearing from companies that they have to get approvals for serverless, but it's something that, everyone is really excited about. There's three major things that you get with serverless with DLT. One is simple development, simple operations, and I'll talk about those things in detail. In development, you get declarative APIs, not just streaming tables, flows, and syncs, and materialized views, but also CDC APIs and data quality. That makes it really, really easy to do things that are otherwise require a ton of code and boilerplate code. Serverless DLT also provides the best possible performance. There are new optimizations that we've built, both for streaming ingestion and for the incremental refresh of materialized views that end up giving you 5-6 times better performance for the same exact pipeline. And we're gonna share some benchmarks that we've done as well on that. And then finally, we're able to get all that better performance at a lower TCO than DLT with classic compute. So when I say TCO, I mean, DBUs plus your cloud costs. Serverless will end up being a little bit cheaper than that too. And so we'll talk about how we do that and some of the new metering things that we've built to make that possible. So let's dive into the simplicity story. So organizations continue to tell us that data quality is still a big problem. Organizations suffer from low trust in their data. And often data quality problems are found too late when they've already made their way into downstream reports, and they take too long to fix. So the result is, you're showing incorrect data to your company, to your customers, to your partners on your website, and then your pipelines are down for a long period of time. Like I'm sure a lot of us in this room, myself included, have taken pipelines down because there's a data quality problem, and you don't want to start it again until you've backfilled the data, you've corrected it, you've fixed the source upstream. So that's why DLT includes first-class support for a concept called expectations. These are in SQL, you can define expectations as constraints. In Python, there's an expect function. And you can create an expression that will be evaluated for every single value in that row. And it's evaluated in real time. It's using the structured streaming observe operator. So it doesn't have to reread all your data after it's written. You can do it in real time, so it's super efficient and fast. And you can decide on what to do if that expression evaluates to false. So by default, you can the simplest thing that you can do is just retain the row and log it so that you can look back in time and say, oh, this many rows failed that expression, but the data will continue to flow. You can choose to drop that record and quarantine it, put it aside, and not have it go through. Or you can tell us to stop the pipeline entirely, in which case the pipeline won't start again until that expectation sort of passes and the data changes. All of this information can be observed in the event log for DLT and also in the UI, where for each expectation, for each table, we'll show you statistics about how many rows were evaluated, how many were dropped for each of your expressions. So let's talk about changes now, stream processing and change data capture. What if you have changes in your data set? Like what if you're ingesting, or you're trying to replicate a database from some external system and you have a change data feed like from Amazon DMS or Golden Gate, or you are receiving an event stream of information about your customers and you want to keep a target up to date with all of the properties of that particular customer. So previously, the way to handle this is with the merge into API, right? You're just looking at that data and you're writing code to handle updates to your data set. This is really complicated, especially when you have out of order issues. Like these message buses don't guarantee in order data, so you have to deal with ordering. Some of these applications don't give you all the data. They'll give you null values inside of fields to save bandwidth, so they'll only show you data when the data has changed, which means you have to keep a log of what the data, of what the value was. And this is really, really hard to manage. We've seen implementations of 300 lines of code just to handle a really simple SED type 1. And so that's why we built the apply changes into API, which allows you to do all this in a declarative way. So All you have to do is you tell us the keys that indicate the uniqueness of your row, the conditions upon which to delete a row, the sequence by column. It can be a timestamp or anything, and then how you want to store the data. And then we will handle the merging, the updating for you and guarantee that it's correct. So that's great for streaming. We don't always have a streaming source. Sometimes we just get full snapshots into a cloud storage bucket from some weird external database, and we want to materialize those snapshots into our target table. Well, we offer support for that too. There's a new feature that's coming into public preview very, very soon that works the exact same way as apply changes into. It's called apply changes from snapshot, and it's just that. You have to, so it's got the same API, but you have to tell us two things. You have to give us a pointer to a data frame of your full snapshot, and you got to make sure it's really full, or it's a full snapshot, because if we see a row that's missing, we'll assume that it was deleted. And then you also have to tell us the order of those snapshots so we can figure out if a row was deleted, whether it came after or before the previous one. So this is something that is really useful if you want to easily avoid writing all of that code yourself. So look at the files and do the diffs and then write the merge statements. And we do it all very, very efficiently. So slowly changing dimension type 2 is a really powerful capability. It's available for both batch and streaming CDC APIs and Delta Live tables. And it's useful for applications in like financial services, health sciences, where you need to keep a history of all rows that have been updated. So by default, when we see a row that's updated, SCD type 1, we'll just replace the row and the old value is gone forever. By changing one line in your apply changes stanza to say SCD type 2, the system will add 2 additional columns, starts at and ends at. Those columns will take the type of your sequence at column. So if it's a timestamp, it'll be a timestamp. If it's an integer, it'll be an integer. And the latest value always has a null field in the ends at column. So you can create a view on top of this table and just have a table, a view that only shows the most recent data. But then you can go back and look at all the previous values. Whenever we see an update, we'll add the updated time in the ends at column for that row so you can keep track of history for all time. Again, really hard to build yourself. Highly recommend you don't try, just use apply changes into for that. So let's sort of shift over to operations. So our goal with DLT has always been to make it so that you don't have to worry about operations or resource management. Sizing clusters is really hard. It's really hard to avoid over-provisioning clusters for horizontal scaling. For Delta Live tables, we've had this enhanced auto-scaling capability that does a much better job than the traditional clusters auto-scaling of dealing with streaming and spiky ingest, streaming data workloads. So it does a really good job of only scaling up when needed, shutting down when it can shut down safely in order to take down resources that are underutilized. And this is a capability that comes by default with DLT. New in serverless is a vertical auto-scaling capability. So this solves the problem of out-of-memory issues. So, sometimes your transformations or you have a streaming table with a really long watermark. It takes up more memory than is available to the core, to the slot that's processing that transformation, which leads to an outage. You have to go in, you have to increase the instance size, restart. We've built technology that will automatically detect those OOMs. It'll restart the system for you with one higher class of instance type in serverless so that we can recover from that outer memory error. And it'll remember the next time we start that pipeline to use that. It'll also go down again. If we detect very, very little memory pressure or a lot of unutilized memory, we'll actually go back down to the smaller instance size as well. You'll still see a restart, but you won't have to deal with any of the manual intervention to get back up and running, and over time we'll improve that as well. Now, Delta Live Tables has always been versionless. We've always had current and preview channels. You've never been able to pick a DBR version in DLT, but I wanted to talk a little bit about some improvements that we've made to how we handle service upgrades whenever we're upgrading the DBR version in your channel. Now, the goal is to always make sure that your pipeline is up, that it's never down for a long period of time. We have a process that we call health-mediated releases, whereby we will always make sure that your pipeline is running the last known good version of the runtime. And if we try to upgrade you and we see a failure, we'll roll you back, we'll pin you to that previous version. A backline engineer will be paged and look at your system, deploy a fix if it's a problem on our side, and upgrade you. Sometimes it's a problem on your side, so we'll reach out to you. This is often the case if you have init scripts and there's an issue with starting up. And that is something that we're always improving, but it's really, really helpful to know that you'll always have your pipelines up and running as much as possible. Now, in addition to service upgrades and scaling, DLT also handles a number of other things. So because we've had so many years of experience with running streaming pipelines, we kind of know what are the best defaults to choose for Spark. Spark has a lot of options, so we can set those for you, like optimized writes, auto compaction. We also physically manage the layout of your data, so we'll run vacuum and analyze and optimize on your data sets. You can still use cluster by and Z-order. We also handle schema evolution automatically too. So if you have an MV, adding, renaming, and removing a column will behave as expected. For a streaming table, if you add a column, we'll add that column and then have nulls in the previous values. Or if you take away a column, we'll keep sort of the old data there for you. So that is all handled automatically where you won't need to stop the pipeline and take any action. So observability is also really, really important. Delta Live Tables in the Databricks UI, has an operational dashboard. It's sort of a nerve center where you can see what's going on, you can take action on your pipeline, you can modify the pipeline settings. The first thing that you'll see is the graph. Like I mentioned earlier, this graph emerges from your source code. So you don't create this graph, you write code and then we create this graph for you. You can click on the items on the graph and then you can see data quality statistics and other metadata about that particular table. You can jump to Catalog Explorer. You can, in this example, the data quality is really good. You can also control your pipeline from the top right corner as well. You can restart, stop, fully refresh everything. You can refresh just a single table if you'd like by clicking on the table and refreshing only that one. The event log is on the bottom. That's the real-time log of telemetry and lineage for the pipeline, and where you can also debug. Now, that's all great. We're not all kind of always going to be in the UI all the time. So the event log is something where we can build reports on and generate alerts off of. It includes three things: telemetry about your pipeline. So there's a time series of the pipeline operations, the configurations and settings at that time, how many rows were processed, incremental refresh status. You have lineage data going back to all time so that you can keep track of the history of lineage, and then all the data quality statistics that we talked about. So you can see for each expectation, for each table, the pass, fail, drop statistics that you can also create reports on. There's also many capabilities to send you alerts when there's issues. So we have integrations using, if you use jobs to schedule the pipeline, you can get email notifications for failures or retries, to PagerDuty, webhooks, to Slack. And then there's a new capability called event hooks, where you can write some Python code in your pipeline to ship the event log or custom metrics from the event log to your favorite tool, like a Datadog or Splunk or Grafana. So let's shift gears and talk about some of the new performance benefits of serverless DLT. So you have a few options in scheduling pipelines. So there's an inherent trade-off between data freshness and cost. On the one hand, with DLT, you can pick continuous pipelines. These have compute deployed all the time, and they're running really, really as fast as possible. So this is where you want the best latency at any cost. On the other hand, you can schedule pipelines using jobs or your tool of choice, and the cost then will vary depending on what your scheduler frequency is. One of the exciting new capabilities that's available only in serverless Delta Live Tables is the ability to incrementally refresh materialized views. This uses a cost-based optimizer that we call Enzyme. And the way that it works is that you can define any query for your MV. At the time that we go to refresh your materialized view, we'll use a cost-based model to determine what's the most optimal way to refresh the materialized view. So we'll look at the query plan, the data, the nature of the data change, of the changes to the data, and we'll pick the best technique. So for example, if we've only seen inserts to your data and you don't have any aggregations or anything, then we'll just do like inserts to the MV, really easy. If you have co-partitioned your materialized view with your, and they share the same key as your base tables, we might just drop that partition and then just recreate that partition. Or we'll do merges if that's the most efficient thing. We'll fall back to full recompute if none of those techniques are available. We're always building new techniques and adding new techniques to Enzyme, and our goal is over the fullness of time is to support every single query that you write. But my advice is just write your queries with MVs and trust that over time they'll get faster as we improve the engine. Managed file events is also a new serverless capability that streaming tables can take advantage of. Now, as I mentioned earlier, streaming tables use the autoloader under the hood to ingest data from cloud storage. The default way of determining when new files have arrived is to list out that directory. Obviously, if you have a lot of files, that list process is really takes up a lot of time, which impacts latency of your ingestion. So with managed file events, Databricks will will configure a message queue for you and consume those events so that we can detect when new files arrive and get like a push event from your cloud storage provider so that we can ingest data much more efficiently. You can enable this with just a single line of code. You can't really see it here, but in your streaming table configuration, you just have to add one line of code. Stream pipelining allows for much faster ingestion. This is also a serverless-only capability. It improves throughput. Previously, in structured streaming, it was difficult to fully utilize your compute because some tasks finished first, leaving other tasks slots idle while the slowest ones finished. With stream pipelining, it solves this by enabling structured streaming to concurrently process microbatches. So ultimately, this leads to significant improvements in ingesting files using streaming tables. And this is sort of on by default. All right, let's talk about low TCO. So I'm excited to talk to you about this. So if you've used Databricks for a while, you're probably obsessed with looking at the efficiency of your instance. You're constantly looking at metrics to look at memory pressure, CPU utilization. You're always looking to see, are you using as much of the capacity as possible? Because you're gonna pay for the instance no matter what, whether it's used all the way or not, right? So you're always sort of keeping track of utilization. It's a huge pain in the butt to change instance types and to manage that process. All that goes away with serverless, because with serverless, you're only paying for the slots that we launch for your tasks. Databricks pays for unused slots in the instances that we launch for you on your behalf in serverless. This ultimately leads to much less utilization of DBUs and much more, and it's really truly a pay-as-you-go model. The other really nice thing is that the cost of a DBU in serverless DLT is the exact same as the cost of a DBU in serverless jobs and serverless interactive notebooks. So we've aligned all the costs across all those serverless products using a new SKU. So you no longer have to think about the price when choosing between DLT or jobs for your ETL workloads. So now I'm going to invite my colleague Kiavash to share some benchmark results related to TCO and performance. Thank you.
Thank you. Can I have it?
Yes, go ahead.
Hey, hi everyone. Thanks, Paul. So I'm Kiavash, an engineer on the DLT team at Databricks. So Paul mentioned that one of the major advantages of DLT serverless is its superior price performance. So I'm here to present to you the result of two benchmark experiments that we have done to compare the price performance of DLT serverless with the classic DLT. So let's dive in. So the first experiment we have done is ingesting 100,000 JSON files into a streaming table. So we have a simple pipeline which does this. And the total data is about 2 terabytes. And we ran this experiment multiple times using classic DLT with these configurations here. We use a default instance type. We use enhanced auto-scaling with a maximum of 64 workers. And we had the photon off. And we then run the same pipeline using serverless DLT. Again, collecting the information about the cost and the throughput. So let's look at the results. So this is a plot that shows all the runs in terms of cost versus throughput. Horizontal axis is throughput. The vertical axis is the cost. And the blue dots corresponds to serverless DLT. Red dot corresponds to classic DLT. As you can see, there's significant improvement in throughput. And also, while I'm getting less TCO for serverless DLT. So it has both advantages here. So zooming in into throughput, looking at the median of the data that I showed in the previous slide, in this experiment of loading the streaming table, we have a 4 times better throughput with serverless DLT compared to classic DLT. Paul talked about the stream pipelining. So one of the major reasons behind this is that stream pipelining that results in, which is exclusive to serverless and results in high parallelization of the ingestion process in streaming. So that's great, but you can get this great improvement in throughput actually with cheaper TCO. So actually we have a 32% less cost on serverless DLT here. As you can see, classic DLT has the DBU cost in addition to the red chunk, which is the cost that needs to be paid to the cloud provider for the instances. But the serverless DLT is just a DBU cost because we at Databricks create and manage and pay for the instances, so the customer doesn't need to do that. So putting both metrics together, price and performance, if I divide the total cost by the throughput, I get a price performance for 5 times better for serverless DLT compared to classic DLT. So one way to look at that is that if I get the same throughput from the two systems, classic and serverless, serverless is going to be 5 times cheaper. Or you can look at it from the other perspective. If you pay the same amount of money on the two platforms of compute, you are going to get 5 times faster throughput in serverless compared to the DLT. So that's awesome. We did another experiment looking at a materials view refresh benchmark. So here I'm creating a materialized view. I have there's a pipeline. I have a source table which has 200 billion rows. And these 200 billion rows are over about 2 billion unique keys. And that unique keys, in this case, as shown in the query on the right, is the customer ID. And what I want to do in this materials view is to do an aggregate, a bunch of aggregates over another column called amount, like mean, max, average, or sum. And create this materialized view that gives the aggregates over the customer ID. So in this experiment, we ran, each run was done in 4 updates. So the first update, which is the first run of the pipeline, creates and loads the material as we do, so reads all the data and calculates the aggregates. And then we do the subsequent updates as refreshes by inserting 1,000 new rows in the source data and then recalculating the aggregates. So the way we did the setup is the same again, DLT Classic with the same configuration as the first experiment versus the serverless DLT. So let's look at the results of cost and throughput. Here, I'm going to look at the first update separately and then go at the subsequent update. First update is the one that does essentially a full refresh and loads all the data and calculates the aggregates. So again here, I'm seeing a similar picture. Higher throughput significantly and significant less cost. If you look at the cost, actually, it's going to be 45% less this time for DLT serverless. And the throughput is 2 times higher. This is for the first initial loading. Which another way to look at it is this 50% lower latency, which results in 2 times fresher data when you are creating this materialized view aggregation. And but the things becomes even more exciting when you go to the subsequent updates, because here is where the incremental refresh that is exclusive to DLT serverless kicks in. So yeah, this is just the 4 times price performance from the first update, which if we put the price and performance next together, I get about 4 times better. This is for the initial loading. Now this is for the subsequent updates. Here, as you can see, the classic DLT almost has the same about the same cost and throughput when you are just inserting another 1,000 row into your source table and refreshing the aggregates, because in classic DLT things are being fully refreshed again. But with incremental refresh that we have in serverless DLT, you get way better throughput with close to 0 cost for updating the aggregates over these 200 billion rows. So zooming in, actually it costs me only $1 to do this update of after I insert 1,000 rows into that 2 billion row table, because things are being just incrementally calculated, while the cost for the classic is just about the same because of the full refresh. And the throughput is much better also, 6.5 times, 85% lower latency. So therefore, your data is going to be way fresher if you go with serverless DLT. Putting both together, I get a huge improvement in price performance, 340 times better over classic DLT for just keeping refreshing this MV, which is awesome. And again, this is due to the serverless exclusive technology that incrementally refreshes the MV versus the classic DLT, in which every update is essentially the same as is fully refreshed and is equivalent to the initial update. But don't take our word for it. You can recreate these experiments in your environment. We have put the data generation code and the notebook for these experiments at this link, available, accessible through this QR code. And just give it a try. And I want to end with a note that it's true that the experiments we have done here are using simple building blocks of larger pipelines. So we have single table pipelines, but the technology that goes into these speed ups and lower cost applies to the larger pipelines, because They are composed of these building blocks, so we expect similar types of improvements on larger pipelines also. And we're going to share more results about that over time, I'm sure. Thank you very much.
Well, thank you, Kivash. $1 per update. That means I can do 8 refreshes for the cost of 1 cold brew in San Francisco. So I want to now talk about developing with DLT. For many of us that have worked with DLT, the development experience in the notebook has not been as great as we'd like it. We've been investing a lot in that over the past year. So I want to take a step back and talk a little bit about how to, sort of how to think about getting started with DLT if you're new. You just have to create a file and just start creating your transformations in that file. Start writing, create streaming table for ingestion, create materialized views, and using Python or SQL. You go to the DLT page, create a pipeline. If you have serverless enabled, click on the serverless button, and then just click start. And that's really it. DLT will look at your source code, run the tables in the correct order, and you'll see a log when everything is finished. Now, I'm really excited to announce, coming very, very soon this summer, we're launching a capability called direct publishing. For those of you that have been using Delta Live tables, you've been limited to publishing all of the data for your tables into a single schema, into a single catalog, into a single schema. We're changing that. We're changing 2 things. Number 1 is we're going to give you the ability to indicate the target for every single table in your pipeline when you create the table. So in this example, you're creating a streaming table in catalog 1, schema 1, table 1, and then V in a whole different catalog, schema 2, table 2. And then you can read from other tables in DLT. We're doing away with the requirement to use the live keyword in DLT. So you can just write your code as is, and we'll infer everything automatically for you. We're really excited about this capability because it's going to make it really easy for you to send data to the appropriate location when your organization has specific places where data should go. So please look out for announcements related to this soon. Now, developing and testing pipelines to catch issues early is hard. Really, it requires you're implementing software engineering best practices. One of the main things that you need to be able to do is run a version of your production pipeline in an isolated environment so that you can make changes to the code of your pipeline and test them before you promote them to production. DLT gives you certain tools to be able to do that. There's 2 things I wanted to talk about here. One is, because every pipeline has a setting, you can pass key value pairs into the pipeline settings. In that way, you can parameterize your pipeline. You can take the keys and values and interpolate them into your source code. So you can use that information to pull data from a different staging environment, for example. The second thing it gives you is the ability to control where data gets sent. So the same source and so the same pipeline code can persist data to a different schema so that you can isolate where the data that is written by your test and dev pipeline so that they don't impact production. So, building all this yourself, especially with SQL, is really, really hard. So you get all this ability to parameterize your pipelines really easily and out of the box with DLT. Now, Databricks Asset Bundles is a new capability that's Databricks-wide. It's the single place where you can define resources in a single YAML file for all of your jobs, DLTs, ML models, and notebooks. So it gives you the ability to do version control, code review, testing. That makes it possible to really describe any Databricks resource across the whole platform. So end to end, you can define your entire workflow from DLT along with jobs in a single place. Really makes it easy to collaborate with other team members. If you haven't checked it out yet, please go look at our documentation. So now I want to introduce Dominic, who's going to give us a demo of all the new cool features that we've released in the notebook for developing Delta Live tables. Thank you, sir.
I'm excited to share with you how now it's easier than ever to build DLT pipelines. And I think the best way we can do that is to actually build a pipeline together. So what should we build? So lately I've been interested in exoplanets. Those are planets outside of our solar system, and I'm curious which ones are actually similar to our Earth. Similar mass, temperature, and radius. And so let's pull in some data from NASA and actually see what we can build. Is it running? All right, so I have some NASA data here, and I already loaded it into the Unity catalog. We have many columns in our data set, but we're only interested in the mass, temperature, and radius, and we're going to build an ETL pipeline to analyze this data. Again, to look for Earth-like planets. We'll call it exoplanets, and we'll need to make sure we specify the Unity catalog where we place our data so we can access it. When we click Create Pipeline, we didn't actually give it a notebook. So it asks us, do we want a notebook automatically created for us, a blank one? And that's a great idea. Let's click Create Pipeline. Now we have our empty pipeline, and we can just click on the link, and we're now in our source code. We have an empty notebook here. And right away we're asked, do you want to connect to the pipeline exoplanets, the one we just created? So let's do that. Now what does that mean? That means that now we're in like a DLT mode, and if we go to the compute dropdown, what we see is, in addition to the compute that we would normally see, we also see pipelines. The pipelines listed here are pipelines that are associated with this notebook. That means pipelines that have this notebook as a source code. And right now, the only one is exoplanets, the one we just created. And if we look at the connected status of exoplanets, we'll be able to detach, reattach, and also open the DLT UI if we want to go into an operational view. Detaching goes back to like the regular compute if you would like to do that. So in this mode, you'll notice we have a few things. We have a validate button, a start button, the DLT graph, and the event log. And the start button will allow us to start an update like you normally would. And validate, what that does is it's like starting an update, but it doesn't actually run data through your pipeline. So it'll allow you to really easily catch errors without having to run all your data through the pipeline. The event log looks like you've seen in regular DLT UI, and we have your graph that you can use. Before getting started more, let's kind of move things around a little bit, make a little bit more space. I like having more space. And the first thing we're going to need to do is pull in our data from our data set, our NASA data set, and we're going to want to process it a little bit. Right now, it's kind of in a state where there's like a lot of data there, and we're only going to want to look at a few things. And to help me do that, I'm going to ask the assistant to help. So I'll prompt the assistant with what I want it to do. And in particular, what I want it to do is I want it to read, using Python, a streaming table from Unity catalog, and I explicitly want it to be that data that we just loaded in. I only want a few columns though. I only want the mass, the temperature, the radius, and the name, because that's all I'm really interested in. And I also need to aggregate all the rows that have the same name and average all the data together. And this is because for a given exoplanet, there could be multiple studies that talk about an exoplanet. Some studies have the mass, some studies have the radius, sometimes they have both. We want to average it all together. It's not too scientific, but it's just giving us an idea. And then I want to rename some of the columns. They're kind of hard to read for me. I'd like to call them relative Earth mass, relative Earth radius, temperature Kelvin, because that's what the temperature is in. And I also want to make sure I have any imports that I need covered, and I want everything in a single expression. I don't want to have a large code block. So I'm being very precise, the assistant telling me exactly what I want, and now let's see what it tells us. So it's telling us what we want, showing us exactly how to read from Spark. So if you weren't too familiar with Spark, we have our code right there, imports and everything. And so let's make our table. Our first table is just going to have the data pulled in. And we'll call that exoplanets processed because we're processing the data we have on exoplanets. And we'll just return the code that we have. And we'll also need to make sure we import the required import, otherwise it's not going to work. And the assistant was kind enough to give us that import, so we might as well use it. So now we could start the pipeline and see if it's working like we want to, but let's click validate. So again, that's going to do what Start normally would, but it's not going to actually run data through it. It's very fast. And if you look, it's initializing as red, it means there's an error. And so we could click on the event log like you would do in a regular UI and see the DLT is not defined, or you notice the DLT is underlined in red, showing us exactly where the error is. We can highlight over it and see that DLT is not found. We forgot to import DLT. I always forget to import DLT. I'm in DLT mode all the time. And so our code should be working. We see the red squiggly line goes away. And so we could validate it again, make sure it's working, but it's probably going to work. Let's work on our next table. And what's our next table going to be? We're going to want to take that process data and then only look at the rows that have actual valid data for the mass, temperature, and radius. So I already did some analysis, and some of the rows have nulls for that. Some of them may not be valid, and we want to get rid of them. So we're going to do DLT.table. We see the assistant suggesting DLT.table there. And as I type DLT, we have drop-downs now that appear that show exactly what's available. We see expect or fail, expect or drop, and we want to drop table or drop rows that don't match what we want. In particular, the assistant gave us a suggestion, not quite the best suggestion in this case. What we want to do is we want to make sure the mass is valid. So we're going to say we want relative Earth mass. We want it to be not null, and we want it to be positive. So we only want to look at those rows and drop the ones that don't have that. We also want to do the similar thing for the temperature, or for the radius. And so we're going to write the same type of code and do the same thing for the temperature. And again, pushing control space, or just waiting on a dot, we get that drop down of what's available for functionality. Now, as we're typing here, the assistant's thinking, okay, how can I help? And it suggests, maybe you want this text. This is exactly what I want. So we can just push tab and we have the text there. Now, what should we call this? We'll call this just exoplanets, because these are the exoplanets that we're interested in. And we're going to do DLT.read, again, using the dropdown to do the read. And then the assistant's going to suggest, maybe you want to read exoplanets process. That's the table that you had already, and that's exactly what we want. Now, I could click validate here, click the validate button to see if this is all working like I want to, but instead, I'm going to push shift and enter. The thing that would normally run a cell validates a pipeline when you push shift enter. And we see we have an error. Again, it's underlined in red, and it's called exoplanets here. It was failed to resolve because the name relative Earth mass is unknown. And we see it's giving us suggestions. Relative Earth mass is spelled wrong, so let's just click that, correct that. Click validate again. Again, it's checking if our graph looks like it's supposed to, and we see that it does. We have our original exoplanets that are processed, that's feeding into our exoplanets next table, and we see it has the columns like we expect if we click on the entries, or the items in the graph. All right, so let's move on now. And to find Earth-like planets, we got to find the planets that are Earth-like mass, Earth-like radius, and Earth-like temperature. Not very scientific, but we'll just say if it's Earth-like radius, if it's kind of similar radius to the relative to the Earth, same with the mass and with the temperature. The temperatures there I kind of just picked. It's about between 4 degrees Celsius and 27, like 40 degrees Fahrenheit to 80. Pretty good temperature, not too bad. So let's click start, because we actually want to see data go through the graph to see if any planets actually match this. If we click validate, we'd see the shape of the graph. We actually want to see if any data goes through. Oh, again, we have an error, and it's saying, if we scroll down, it's saying it's failed to read the data set exoplanet. So I'm not having a really great day here. I keep mistyping things, right? But the thing is, the tooling here is helping me to find those mistakes much quicker. I don't have, if you notice, we only just really ran the update right now to get data going through the pipeline. Everything else, we just validated it to see if it was working like it's supposed to. So we see we have a few planets matching criteria. We only have 7 with a temperature, so apparently a lot of planets out there don't have very nice temperatures. And so we'll move on to the last data set that we're going to be working on. And again, we had the autocomplete, we had the assistant, we have validate and start, all within the notebook, along with the graph and event log to help us author our code. We never had to leave this experience, and we could just keep going working on our pipeline. So the last table we have is just going to intersect all the previous tables, because that's the planets that have all 3. And what I did is I clicked Shift Enter, and I pushed Shift Enter again, because immediately after push Shift Enter, I recognize, oh, I forgot a T in intersect. So if you push Shift Enter again, it's going to stop the validate and start it up for you again. So if you're typing in the moment, you don't have to move your mouse around. You just keep pushing Shift Enter as you fix things. Now we're starting the pipeline, watching the data go through. Right, so the data is processing through again. Again, the first table is streaming table, and the rest are materialized views. And now let's see what we get. See how many planets we find. All right. Okay, one planet. So of all the planets out there, there's approximately 5,000. One planet matched all these criteria, at least the way we calculated things. Let's figure out what that planet is. So what we can do is go up to the compute, drop down and go to the operational UI. We can click on the last table there. And from there, we can click on the table link, and it'll take us into Unity Catalog. Remember, this is where our data was. We can click on sample data, and since there's only one row, the sample data is all the data. And it's K2-3D, so that turns out to be the planet that we found. So let's do a Google search, and this is actually NASA's website for the Exoplanet Archive. And this is our planet. It's a rocky world, larger than Earth, 144 light years away. So it takes 144 years for light to get there. So if we looked at the planet now, we're actually seeing it 144 years ago. And the interesting thing is, if you wanted to go by, let's say, commercial jet, and you wanted to fly there, it would take 200 million years. That's quite a distance away, so probably not going to be going there. And so we found our planet, and we did it building a DLT pipeline. And we did it pretty quickly, pretty easily, by using the features we had. We had validate, we were able to see the graph, the event log, and we were able to see data kind of flowing through there and finding out exactly kind of what our graph looks like and how much data we're processing. And so I'm really excited to share this with you, and I'm hoping this will really help everyone build their pipelines and build them more quickly, more efficiently, and more painlessly. Thank you.
Thank you, Dominic. Well, DLT can do everything for data engineering, but it can't get you to that planet in your lifetime. Thank you very much. So that's the end of the presentation. I wanted to call out some talks that you may be interested in if you want to learn more about data engineering. I think at 4 o'clock downstairs, my colleague Ryan is talking about streaming and Project Lightspeed. Then later, Zoe is talking about like more of a high-level primer of DLT with Heineken, one of our customers. And then tomorrow morning, please join the keynote where we're talking about Lakeflow and some of the new announcements that we're launching. And then the ingestion connectors talk is at 11:30 tomorrow, where Elise will talk about our new announcements around Lakeflow Connect. Thank you very much. Would really appreciate if you could log into your app and rate this talk. The events app is in that QR code as well. Thank you very much for your time, and we'll be hanging out here if you have any questions for the team before you go. Thank you.